Hello, in this second video I will show you how you can parallelize any agent over multiple processes to speed up your computation and handle large-scale computations. To show you how to do that, I will use exactly the same examples than the one in the previous video. Okay, so let me restart from the code of the previous video. So remember, what we are doing is computing a variable a defined like this, a variable b defined like this, and then a variable c, which is the sum of a and b. Okay. In order to do this, we have defined an a agent computing values at each time step, a b agent computing values at each time step, and a c agent which is able to do the sum of a plus b. Okay. Here the C agent is working at each time step, and we have another implementation of the C agent which is doing a global computation over all the time steps. Okay. I will just keep the second one and call it C. First, let us forget about this C value and focus on A and B. So remember, to compute A and B, what we do is that we define agent A, agent B. We combine these two agents into one single agent that will execute agent A and then agent B. And then we combine this agent, we encapsulate this agent into a temporal agent such that it will be executed at each time step. Then when I want to execute this agent AB, I can execute it on a workspace for a particular number of time steps. And then I will print what I have in the workspace. So let me execute this simple code here. And what I see that after the computation, I have one variable of size 100 time step times 32 batch dimension, and B is 100 time step times 32 batch dimension. Remember also that this 32 batch dimension is coming from the fact that when we compute the first value of A, we have decided to compute a vector of size 32, and this size is a batch dimension of our computation. Okay. Now, what we would like to do is to do exactly the same computation, but instead of computing A and B into one single process, we would like to compute A and B into multiple processes to speed up this computation. In order to do that, we need to use the multiprocessing abilities of Python. And when you use multiprocessing in Python, what you have to do is to do it like this, because you want to avoid, when creating new processes, to re-execute the same code. So it's just exactly the same code, but with this if to avoid executing the code in multiple processes. Okay. So here I have my agent and my workspace, and I execute my agent over the workspace. What I will do is that I will write this a little bit differently. I will, from this agent, I will create my remote agent, my multiprocesses agent, and then I will also create a multiprocesses workspace by using the create function of the nRemote agent. And this create function will take as an input the agent I want to parallelize, the number of processes on which I want to parallelize this agent. So here I will create 4 processes. And then you will also take as an input the argument used to execute this agent. So this remote agent is one of the agents we provide with SaLinA. Okay. And here, by executing create, you will create multiple processes. What you have to understand is that the way it is creating this new agent and new workspace is by first executing this agent over an empty workspace. This is why we need to specify this argument is because before creating the processes, there is one execution of the agent to capture the size of the tensors that will be created by this agent. So when you use a classical workspace, you can do whatever you want, and the size of the workspace will adapt to what the agents are computing. When you use a remote agent, you want to have a fixed size for the tensor into the workspace because these tensors are in shared memory. So you need to execute the agent, capture the size of the tensors that are created in the workspace, and then from this size, it is possible to create a shared workspace here. But then I have an agent, I have a workspace, so what I can do is exactly the same stuff. I can use my agent like the previous one. I can execute my agent over this workspace with some arguments. So for instance, these arguments, but not that I can change, for instance, this value. Okay, since it will not change the size of the tensors, I can perfectly change some values when executing the agent. And then I can print the output of this remote workspace. Let me execute this code. When creating a remote agent, I also have to specify the seed of this agent. Actually, when you define agent, you have to define the seed of each agent you are defining, because your agent, we assume in SaLinA that the agents can be stochastic. And this is particularly true for the remote agent because it is mandatory for the remote agent. Let me execute this script. So that what you can see is that the system is creating 4 processes, and then at the end in the workspace, what I obtain is still 2 variables, A and B. The size of these variables is 100 times steps times 128 batch dimension. So why is it 128? It is because we have executed over 100 times steps. We have executed 4 copies of this agent, and since each agent is producing a batch size of size 32, at the end we obtain a batch size of size 32 times 4, which is 128. Okay. If I want to do it well, I'll also have at the end to delete this remote agent in order to close the different processes. Okay. And then you can see that the system will automatically close the different processes, the 4 processes we have created. Okay. And what is nice with SaLinA is that, okay, you have to create this remote agent, but once it is created, you can use it exactly like any other agent. So it's very simple to take an agent and replace it by a multi-processes version of this agent when you are doing complex computations. There is one more thing you need to know about remote agents. The way right now remote agent is implemented in SaLinA, it is by using tensors in shared memory. So first, when you compute over a remote workspace, you will lose all the gradient information. And in the next videos, I will show you how you can get gradient when using agent in multiple processes. But then also, what you have to understand is that right now on this remote workspace, if I try to execute my agent C, so let me define my agent C. So it is a C. Okay. Remember that this agent is creating a new variable in the workspace. So the way I'm using it, the natural way to use it is just to do this like that. But if I do this and I execute, you will see that I will have an error in my execution. Okay. And this error comes from the fact that since the remote workspace is a workspace in shared memory, it is not possible in this workspace to create new variables. Okay, again, this workspace has a fixed size, and it's not possible to modify the size of the variables in this workspace. So this is not working. And in order to make this work, what I have to do is to create a new workspace as a copy of this workspace. Okay, so I create a workspace from this remote workspace, and then I can execute my agent C over this new workspace, because this new workspace is a normal workspace, so I can do whatever I want in it. Okay, and then I have my 3 variables. Okay, so to conclude, first, it is very easy to parallelize an agent on multiple processes. But then when you do it, you have to take care about the fact that you obtain a workspace which is a little bit particular. You cannot change the size of the variable in this workspace. And if you want to change the size of the variable in this workspace, you have to create a new workspace from this remote workspace. Thanks.